Okay, now we want to look at the energy transfer involvement based on the boundary selection. So the energy that include in our analysis actually depend which boundary that we choose for our analysis. Okay, so this involves with the energy transfer by heat and also energy transfer by work. So the keywords of the energy transfer involvement is the energy must cross the boundary. Okay, the energy must cross the boundary. For example, we have an oven. So for the oven, we have the heating element to provide the heat. So we have W electron because electron moving in the heating element wire in order to provide heat in the oven. Q. Okay, so heat will transfer from the heating element to the oven. Okay, let's say we choose this boundary where we refer to the wall of the oven. Okay, so we choose this boundary as our system. So if we look at the keywords of the energy transfer involvement, where we need to make sure that that energy must cross the boundary. So the energy transfer that involved for this system is work transfer, but not heat transfer. Okay, so for this system, due to our boundary selection, we only have the work transfer due to the work electron. Okay, the electron move in the wire of the heating element, and the electron cross the boundary. So we have work transfer. However, no heat transfer because the Q, the heat from the heating element is not cross the boundary. So the heat transfer within the boundary that we choose. Okay, so we need to exclude the involvement of heat transfer for this system. Okay, no Q, no heat transfer for this system. Okay, let's take an example with the same system, but we choose different shape of boundary. Okay, so we have W electron in the heating element, and the heating element will produce heat, Q. And now we choose different shape of boundary where the boundary will not include what I call the heating element. So now if you look based on the keyword of energy must cross the boundary, we only have the heat transfer process for the system without any work transfer. So if you look here, the heat cross the boundary that we choose. However, the work, which is referred to the W electron or electron inside the wire, will not cross the boundary. Okay, so we will have heat transfer Q in our system, but not W electron, okay, or work transfer for this case. So the selection of energy transfer in our system based on the selection of our boundary for the system. Okay, now about the W electron, or we call electrical work. For this electrical work, the electron crossing the boundary and do the electrical work on the system. An electron in a wire move under the effect of electromotive force and doing work. So in terms of symbol that we use for to represent the electrical work is WE, capital letter WE, represent the unit will be kilojoule, represent the electrical work, and small letter WE, the unit will be kilojoule per kg, represent the electrical work per unit mass. And the last one we have WE dot, represent the rate of electrical work or power, that the unit will be kilojoule per second or kilowatt. Okay, in terms of electrical work equation, so we have electrical work equal to V multiplied by N, where V equal to potential difference, which is referred to the voltage, N is the column of electrical charge. So if we refer to the what I call the equation when the value of Vi is not constant, refer to the integration equation. So we have WE, capital letter, equal to integration of Vi with dt from t to t1. So t2 the time for the final state, t1 the time for the initial state. I represent the number of electrical charge flowing per unit time, and delta t is referred as the time interval. Okay, where if vi is constant, so we, the electrical work, is equal to vi multiplied by delta t. Delta t is the time interval. Okay, in terms of rate of electrical work or power, we use this symbol we dot equal to vi, voltage multiplied by I, or the current, the electrical current. Okay, that's how we choose the energy transfer that involve with our system or our analysis based on the boundary selection. Okay, example 3.1. Consider an electric refrigerator located in a room. Determine the direction of the work and heat interactions in or out when the following are taken as the system: A, the content of the refrigerator; B, all parts of the refrigerator including the contents; and C, everything contained within the room during a winter day. So now this question asks you to identify the direction of energy transfer for the system. Okay, for the different boundary selection. Okay, so this figure shows the refrigerator inside a room. Okay, so we have power supply, we have the content of the refrigerator, and also the cold environment outside the room, which is we refer as the surrounding. Okay, now we look at the first case. Okay, where we consider the content, only the content of the refrigerator. So let's say I just take the cold soda can inside the refrigerator. So we choose the what call the boundary for the soda can only. So the boundary of our system just include the content of the refrigerator. So for this case, we have we choose the soda can, okay, inside the refrigerator. So the energy transfer involved is the heat that absorbed by the refrigerant inside the refrigerator in order to reduce the temperature of the soda can. The second one is because what call the refrigerator is open, the door of the refrigerator is open, so we have another heat where the heat released from the soda can to the rooms. Okay, so now the involvement of the energy transfer is only two. First, we have Q out that absorbed by the refrigerant, and the other one is Q that released from the soda can to the environment or to the room. Okay, to the room. Okay, scenario or case number 2, where we need to consider all part of the refrigerator including the content, as shown in this what I call this schematic diagram shows the all part of the refrigerator. So we choose the what I call the bigger boundary that include all part of the refrigerator and also the content. So now the content, what happened to the content already inside the boundary that we select. Okay, now the heat transfer that involved is the heat transfer to the room from the refrigerator. And the another energy transfer is the electron work or electric work from the power supply that transfer into the refrigerator in order to make sure that the refrigerator can be operated, okay, or can be run. Okay, so the only energy that involved for this case, due to the different boundary selection, is Q out to the room, and also W in due to the electric work or due to the electrical work. Okay, so that is the different in terms of energy involvement when we choose different boundary. Okay, the third case is everything contained within the room during a winter day. So now we need to consider the surrounding, the cold environment or the surrounding. So this is the schematic diagram. So we have a room. So inside the room we have refrigerator, and outside the room we have what I call the cold environment due to the winter day. So we need to select new boundary that include the room and also whatever the content inside the room. So the energy that involved is the heat released to surrounding due to the temperature difference. Okay, Q surrounding out. And the other one is the power supply. The electrical work or the electron work due to the power supply to the refrigerator. Okay. So these are the two energy transfer occur when the boundary layer involved with everything contained within the room during a winter day. Okay, so now as a summary, why we not include the other? Okay, for example, for the case number 3, why we not include the other energy transfer such as Q ref out, Q room out, and so on. Okay, so Q room out, Q ref out, Q surrounding out, and also W electric in. So we have 4 different energy transfer. But why we don't choose Q room out and also Q ref out for the case number 3? This is due to our boundary selection. So for Q room out and also Q ref out, the energy not cross the boundary. So the energy transfer within the boundary system. So we cannot include the Q room out and also Q ref out in our analysis. Okay, because this energy not cross the boundary that we select. So the energy that cross the boundary are only the Q surrounding out and also the W electric in. So that's why we need to consider in our analysis the Q surrounding out and also the W electric in. Okay, that's how we select the energy transfer that involved with our analysis based on the boundary selection. Okay, so no Q room out, no Q ref out, because this energy cross the boundary. So we have Q surrounding out because this energy cross the boundary, and also we have W electric in. Okay, because the W electric in cross the boundary. Mechanical form of work. Okay, about the mechanical form of work. So the mechanical form of work actually related to a force acting through a distance. For example, we have a box on a specific surface. So we apply a force to the box, and the box move at certain distance. And for this case, we consider the box is doing work because the process or the system involved is force and also the distance. Okay, there are 2 requirements for work interaction between a system and also its surrounding. First, the force must acting on the boundary. Okay, force acting on boundary. For example, we have a piston cylinder device as shown in the schematic diagram. Okay, we have what called red dash line represent the boundary, and we apply force, okay, to the piston, and the what called the substance inside the cylinder expand. The piston move upward, so we will have what called the piston move at certain distance. So now we have moving boundary for the system, and this moving boundary we consider as the boundary work, where later on we will have specific topic to discuss about the boundary work. And the second requirement is the boundary must move. For example, we have what I call a cylinder piston device, and the piston and the whole system is pulled by using a pulley, and we consider the whole system. We include the whole system in our boundary as shown in the schematic diagram. when we apply a force through the pulley, so the whole system will move at specific height or at specific distance. So this condition, the whole boundary is moved. Okay, both system actually doing work. Okay, so we have the mechanical work. So these are the mechanical form of work. Okay, in terms of work done by a force equation, so the work W capital letter equal to Fs, force multiplied by distance S. Okay, F stand for force acting, and S stand for distance. So if we use the equation involved with integration where the value of force is not constant, so W capital letter equal to integration of F with ds, the distance. And in terms of direction, work done by a system direction, which is referred to the direction out direction. So we can write the work done as the positive value, or we can just type in W out to represent the work done by a system. However, for work done on a system direction, which is we refer the symbol of W or work as the negative value, or we can represent the work done on a system with the symbol of W in. Okay, so this is how we describe the direction of the work done by a system or on a system. Okay, next we have shaft work, where work is the work that related to a rotating shaft. So this figure shows a disc that attached with a shaft, and the second figure shows the dimension of the disc involved with R, S, and also the force, where R equal to the radius of the disc, S refer to the distance, or here if we refer to the circle is equal to the perimeter of the circle, and the shaft work formula will be W shaft equal to force multiplied by S, the distance, where F force equal to T divided by R. T stand for torque, R stand for the radius. And for this case, for the distance for the disc, okay, so we use this equation where S actually equal to the formula of perimeter of the circle multiplied by numbers of revolution of the disc. So S equal to 2 pi R multiplied by N. N is the revolution, numbers of revolution. Also equal to 2 pi N multiplied by T, torque in kilojoule. So in rate form, W shaft dot equal to 2 pi N dot multiplied by T, the unit will be kilowatt, and N dot actually equal to revolution per unit time. Okay, the other mechanical form that we will discuss is about the spring work, where the spring work actually the work that related to a force that applied to a spring. Spring work is the work that related to a force that applied on a spring. Okay, as shown in the figures is the position when there are no force act on the spring. We state as the value is at 0 condition, where no force act to the spring. Let's say we pull the spring at certain by using certain force. So we will have x distance, and this x we refer as the displacement of the spring. The formula that involved is spring for the expansion of very small expansion of spring. We will have delta W spring equal to F multiplied by dx. Okay, F stand for force, X stand for displacement. So F for the spring which is force acting, equal to K multiplied by X. K is the spring constant and X is the displacement of the spring. So in this equation, the distance is presented by the dx. Okay, the dx symbol. Okay, so we make integration to the equation delta W spring equal to F dx. So we will get this equation, spring work W spring equal to half multiplied by K multiplied by X power of 2 or X square. Okay, W spring equal to half multiplied by K multiplied by X square. Okay, for the case where at the initial state we already exert a certain force, so the displacement will represent as x1, and at the final state we exert or we apply more force in order to obtain more displacement. Okay, so x1 is initial displacement and we have x2 initial displacement. So the equation for W spring will be from state 1 to state 2 is equal to half multiplied by K multiplied by bracket x2 square minus x1 square. So these are the important few important mechanical form of work that involved in this chapter, that involved in chapter 3. Okay, example 3.2. A spring whose spring constant is 3.5 kN per centimeter has an initial force of 0.45 kN acting on it. Determine the work in kilojoule required to compress it another 1 cm. This example is just simple example for this spring work. So I will let you to answer this question. However, I will describe a little bit by using this schematic diagram in order to describe the data that are given in the question. So first, the initial condition, actually we already have the what I call the specific displacement for the initial condition, where we need to determine the value of x for the initial condition. Okay, where at the initial condition we have the initial force of 0.45 kN, and the question asks you to determine the work of spring, the spring work, if we want to compress more, if we want to compress another 1 centimeter. Okay, so we want to add 1 centimeter more compared to the initial state or initial condition, and want to know what is the value of force. Okay, when we what I call compress another 1 centimeter. Okay, so what you have to do, first you need to find the value of x for the initial state. Okay, for the initial state you already have the value of f, you already have the value of k, and you can determine the value of x at the initial state. Okay, for the final state you just add, in terms of displacement, you just add the value of x that you calculate for the initial state with the value of 1 centimeter, and then we call use the same equation f equal to kx. The value of k you already have. You just substitute the value of new x, or the x for the we call the final state, that also include the displacement for the initial state, and then from the equation f equal to kx you can obtain the what I call the work that required to compress another 1 centimeter for the final state or final condition for this question. So I will let you to answer the question. Maybe we will discuss during our live session, during the online class and so on. Okay.